I'm going to present investigating steady-state initialization for Modelica models. It's a joint work between me, Olsson, and Erik Henningsson at Dassault System, and the ideas here have been implemented in Dymola and the 3D Experience platform. And well, let's first start by the introduction. Why do we want to find steady state? The first thing is that we start at steady state to simplify analysis, or it can also be a goal in itself, so we can see what the steady state is and how it's influenced by parameter changes, and then we can linearize up the steady state and investigate stability. And it's also interesting for quasi steady state, where some derivatives are non-zero, like a vehicle in motion. And then we have different strategies for finding the steady state. We can symbolically do it by solving the initialization problem with derivatives set to zero, or which we can do either manually by setting them to zero in Modelica, or automated, as we will discuss here. And then it will be symbolically manipulated, but still numerically solved when needed. And then we have dynamic steady state finding. We just simulate until we reach steady state. So let's start with the letter. It was introduced as a flag in Dymola 2022, and it's fairly straightforward. The advantages is that it's simple, easy to use, and it's a useful tool in general. Disadvantages is that it might not converge, because the solution might be unstable, periodic, or there might be strange attractors. Especially double integrators might tend to infinity. And you also get less understanding of a problem. So then we can do the symbolic steady state. I won't think this is trivial, because you just take a normal problem where you have the differential equations and the states equal to the start values, and in steady state instead say the derivatives are equal to zero. However, this might cause structural singularities. It might be singular at the solution, and there are problems with index reduction. And then the normal problem isn't that simple, because you can have some initial equations, and that might cause interference. So we'll look at the basic protocol initialization in Dymola, and we do a prioritized bipartite matching. So we take all the equations on one hand and the variables on the other, and then in priority we take the algebraic variables first, then the derivatives, and last the states in start value priority. And all the states that are not matched, then they are free, so we can set in the default initial values for them. But it's the normal one, and if we have any initial equations, then they are added as well, and similar with fixed start values. So here, if we manually have set up that the derivative should be zero, we add that equation, we get an incidence between it, and we match as previously. It's just that now we get the derivative matched to this x dot equals 0, and there is no free start value to set. And the new method we have, which automatically does this, it's been done before. It's similar. It's just that we take all the same equations, same initial equations, fixed start values. It's just when we match, we do it in a different priority. First do with algebraic variables as before, but then the states, not the derivatives, and we do the states in start value priority. So for the same problem without any initial equation, we get that the derivative is free here, and therefore we can set the derivatives equals to 0, and then we will have to compute the state based on the equations. And that was this is sort of equation for one tank of water and something going out of it. And then we can consider the next case where we have two tanks and the same equation twice, like in this example. And then we see that we get a structure singularity for the derivatives. That is, there are two equations that are the same except a different sign, and that will lead to a singularity. And we handle that not by removing the equation that might be seen as an obvious solution, but instead we add an extra variable with incidence to those two equations and an extra equation, a dummy equation with incidence to the two derivatives. So, and of course we remove the matching, and then we add this extra variable h and the empty equations with incidences in red, and then we do a new matching, and we see that one of the states will be unmatched and one of the derivatives will be unmatched, which means that we can set that state to an arbitrary value and the other state will be computed from it, and we can set the one derivative to 0 and the other will then be computed to be 0 as well. And then we have a next issue is that it's not a structural singularity, it's just a singularity at the solution. So for here we have a density as a function of temperature and pressure, and we have differentiated it. And then in this differentiated equation, there's also temperature and pressure. It's just that we shouldn't solve this equation for temperature or pressure because, well, when in the steady state solution, the temperature and pressure will not influence this because it's multiplied with the temperature derivative, which should be 0. And what we do here is that we modify these incidences to remove those two lines, as you see here, and we only change how we match things. We don't change any of the equations. And after this, then we do the same first symbolic solution and numeric solution if that doesn't work. And then finally we have the last problem here is dynamic state selection. And for dynamic state selection, there are basically two problems. One is that we have to dynamically select which states are active, because those are the ones we should set to 0. And the second part is that when we set some state to 0, then we have differentiated constraints. Like here we have a pendulum, and we have the first and second derivative of that length constraint. And we should ensure that differentiated length constraint is 0. Is automatically fulfilled, because otherwise something is weird. And we solve both of these problems together by, instead of saying we selecting a few derivatives to set to 0, we set all of them in this dummy derivative system to 0. And then we check that the differentiated constraint is automatically fulfilled based on this. So here you can see that if both x dot and y dot is 0, then of course the second equation is 0 equals 0. And if x dot and y dot is 0 and their second derivatives are also 0, then the third equation should also be 0 equals 0. So we add these derivatives, and then we can remove those two equations, and then we have just 3 equations for x, y, and f. And so we can automatically compute that. There's a little caveat that we will return to later. So then we have a quasi-steady state, which is that some derivatives are set and the remainder are set to 0. And the question then is, isn't that just completed? And the answer is no, because we can have this simple example. We have one inertia and a spring and another inertia. We try to set derivatives for the first one and set the second one to 0, and then they will just oscillate. And that's obviously not what we wanted. So we need something more advanced, and we go through some of that in the paper. And one of the simplest ways to handle this is to use this simulate until steady state, because it finds a steady state solution even though it's complicated, as in this case. So here we have a more advanced case with a clutch and bearing friction and driving it, and it converges to a solution, and you see it's quickly found. So let us now go through some examples and see how these three methods work. We take a simple example from MSL with three tanks, and we see first that if we set it up to find the dynamic steady state, it just automatically finds the obvious solution here, and you see that two tanks have the same level, and the third has a higher level to match the different heights of them. And if we try to do it symbolically, we can do it manually, and there is a setting for that in the system setting. However, it will report that there are four consistent overdetermined equations, which is a bit unnerving, but you can understand them. And then the alternative is to say do it automatically, and in that case we have to set initial guess for the system, because otherwise there will be too many. And then we see that there are the three states is one tank level, and the three temperatures once for each tank. And both of these two approaches work, and they give slightly different insights. That is, what are the three parameters and what is overdetermined, etc. So now we take a slightly more complicated example where we mix domains, and in this case we have three springs here and with heat losses in them. And if we try to dynamic steady state, we will find a solution at some point, but it's quite slow because there is a slowly damped oscillation in it. And to do it manually requires some thought, because there's not one setting for this. Automatic symbolic solution, that just works, and you see there's a solid line in the oscillating graphs, and that is the symbolic solution that is just found automatically. And then we take another example. That is, we take a Furuta pendulum. So it's, well, one arm like this with three joint there. And what it automatically finds, well, the first thing is that in order to find a dynamic steady state solution, we need to have dampers in it, because otherwise it will just oscillate forever in a non-periodic way. And if it have dampers, it will find the dynamic steady state solution, and the symbolic can also be found. And then we see that the angle of the first joint is a free value. And we also see that it might find an unstable solution, because it could be like this or like this, and both of them are possible, and it was the same with the pendulum before. So that is one of the disadvantages with the symbolic solution. So conclusions here is that both the symbolic and the dynamic method work, and the dynamic method can be slow if a system is badly damped, etc. Whereas the automatic solution, symbolic, may find unstable solution. The manual is similar, and the problem is that it's more domain specific, and it's often overdetermined. So you have, in general, you have to work a bit more to do it. On the other hand, by working a bit more, you don't find the unstable solutions because you've worked through that in more detail. And quasi steady state is complicated. There's more in the paper, and improving standardization of this would help. And one of the things we do currently is that we automatically remove initial conditions based on settings, because otherwise there are too many settings. So and after completing this, there are more references in the paper, in the actual paper, and of course many of these ideas have been presented before. So if you have any questions, this will now be